In this presentation, I will be covering what segment tree data structures are and how they work. This data structure stores array interval information in tree nodes. It performs efficient range querying, making it useful in applications that require many queries to find specific information of that element included in different intervals of an array. It is also efficient with updating array intervals or segments. They were first introduced by John Bentley in 1974. Some real-world applications are time series databases, like, for example, applications that will allow querying of the minimum temperature recorded in different time intervals. And another real-world application is geometric information systems, like, for example, rectangle intersection detection or polygon clipping applications. There are many types of segment trees based on the range queries they are being used for. For example, there is range minimum query, range maximum query, range sum query, range GCD, range XOR, and range frequency counts. For this presentation, we will focus on range minimum query to explain how segment trees work. We are looking for a data array being stored with n values, and for the sake of this example, n will equal 7. The example we will be doing is RMQ, range minimal queries, meaning making queries of min values determined in intervals of this array and the data array are stored in the leaves of the tree. While each node contains the minimum value of all leaves in the subtree, for example, the value 3 is the min value for all of its subnodes below it. The segment tree structure can be implemented as an array. The values in red are the ones that are stored from the example array. We're now going to look at this example where we have 7 elements. First, we're going to need to reserve memory for an array of size s. From this equation, we know that s is equal to 2 times the next power of 2 greater than n. For this example, we calculate that s equals 16. Then we are able to reserve the memory for an array of that size. We're then just going to store all the values from our array, starting at the center position of the new array, meaning the position of s divided by 2, just 16 divided by 2. Next, we look at every pair on this first level, and we just added and begin populating its parents' nodes. We're going to compare the two values of the pair, and the minimum value of the two becomes the parent node as well. For example, when comparing 3 and 16 over here, 3 is the minimum value of the two, so we populate this parent node with the value of 3. For the array, we populate the values based on the placement they follow in the tree. After comparing all pairs and populating the elements in the tree and the array, we can finally look at the next level of the tree. Over here, we're going to be repeating the same steps, comparing the pairs on this next level of the tree and populating their parents over here with the minimum element of the two. So for example, when comparing 7 and 2, the minimum value would be 2, so the parent would be populated with the value of 2. And then once again, we'll be repeating our same steps, comparing this new level or this next level and populating the root of the tree with the minimum value of the pair. So comparing 3 and 2, the minimum value would be 2, so the root would be populated with the value of 2. And this shows it on the array as well, with the placements following the order of the tree. So comparing position 1 and 2 with values 3 and 2, the minimum value was 2, so the parent node was populated with the value of 2. So now we are done. Our tree is built with each node containing the minimum value of all leaves in its subtree. For our first example, we're going to find what is the minimum value in between positions 1 and 5 of this array. So we're going to be ignoring values 3 and 2 and only looking at positions 16, 8, 4, 27, and 7. We will start with two indexes. There is I, which is pointing at value 16, and j, which is pointing at value 7. We can calculate I with s divided by 2 plus the low range value, which would make I equal to 9. This means that the value 16 is in position 9 in the tree. And for j, we do s divided by 2 plus the high range value, making j equal to 13. So the value of 7 is in position 13 of the tree and array representations. So as of right now, in this range of 16 to 7, the minimum values we have are 16 and 7. Now we don't have to go through the entire tree, we can just check the elements on the level above. So moving forward. So our indexes I and j are now pointing at these two values of the level above the level that we have just looked over. So for I, since it is the lower range index, the pointer moves one level up of the right neighbor. And then for j, since it is the upper right index, the pointer is going to be moved up one level to the left neighbor. Now our new minimums are 4 and 7 since they are the minimum values compared to the elements from the first level. So now we shift the indexes one more time to the level above this previous one. Repeating the same steps, we see the pointers will now actually cross paths, which means that they will stop searching because they have officially found the minimum value between 4 and 7. And the minimum value between 4 and 7 was found to be 4. Now another example is we're going to be finding the minimum value in between positions 0 and 5 of the array. Like the last one, we find the index I pointing at the value 3, which is in position 0 of the array, and index j pointing at value 7, which is position 5 of the array. We're then going to move up a level. So again, the I is now pointing one level up of right neighbor, and j is pointing one level up of left neighbor. The values are still 3 and 7, so the minimum of for now remains 3 and 7. We're going to go ahead and move up one more level. Now when looking up at this new level, when looking up at the level up of right neighbor I and level up of left neighbor j, they both point to 3 now. So from level I, it was pointing right from here to 3, and then from j, it's pointing from 7 to 3. So that means that the value of 3 is our minimum value in the range of the positions 0 to 5 of the array, and we can stop searching. Moving forward, the complexity analysis. For complexity analysis, there is the complexity of building a tree which first populate the leaves. Since there are n items in the array, the complexity would be O(n). Next, populate the upper nodes of the tree. The size of the array is S equals n times 2, so there are n upper nodes to be populated, meaning the complexity is O(n). Therefore, the overall complexity of building a tree is O(n). Then for the complexity of executing a query, first access the position of the interval end is O1, then moving the indexes as many levels up as required until the indexes of the intervals end cross each other. In the worst case scenario, we would need to travel all the way up to the root, which would be O log of n. Because this is a binary tree, the overall complexity of executing a query is O log of n. Now for advantages and disadvantages, the main advantage of using segment trees in range minimum query applications in the complexity order, which is O log of n. Therefore, it is much faster than going through all of the items in an interval to find the minimum value, which is O(n). While the main disadvantage of using segment trees in range minimum query applications is the memory efficient when implementing them as an array. To work with an array, we need to use more than twice of the amount of memory required to store just the initial array without maintaining the information of the tree structure. Now finally, these are my sources that I used to gain my understanding on this data structure